Hi everyone, this is Dr.Hira Khalid, and now we are going to discuss the most common reactions of carboxylic acid, and that is esterification. So, we'll talk about the esterification of carboxylic acid in this lecture. Esterification, basically, in easy way or in a generic form, how we could explain is that this is the conversion of one functionality into another. And what is that functionality is that this is a conversion of an acid into RCOOR prime. So it means that we are replacing this hydroxyl of the carboxylic acid with an alkoxy or any of the OR group. That could be the aromatic as well. So this conversion is called esterification. Now there are the two main methods for the synthesis of the esters, another way, or the conversion of the acids into the esters one. So the first one is the Fischer esterification, and let me say that this is the most common and very efficient in a way, and this is the most easier way to synthesize the esterification. And in most of our lab um, synthesis and most of our research synthesis is also, whenever we are interested for the esters synthesis and the preparation, we go for the Fischer esterification. The second method is the formation of methyl esters using diazomethane. But that involved the very toxic diazomethane. So that's why this has a very limited um, utility, and it is used only when we are very much interested in a way to make the methyl ester of certain carboxylic acid for which we don't have any other way to synthesize efficiently. So now we will go for one each of this esterification method, and we will discuss their mechanisms too. Now the first one is the Fischer esterification, and the Fischer esterification was named as Fischer esterification in the credit of the German chemist Emil Fischer, who was in the era of 1852 to 1919. He was the chemist who developed this method to convert the carboxylic acids into the esters by utilizing the acids and the alcohol. So the process of forming an ester by heating at reflux a carboxylic acid and alcohol in the presence of an acid catalyst. And what kind of acid catalyst we can use is sulfuric acid, HCl, or any of the aromatic sulfonic acids. These are the three most desirable acids for the esterification of carboxylic acids. Uh, in most cases, we prefer to use the sulfuric acid because of the inexpensive, the good availability, and the efficient synthesis and easy handling for our final product. So the sulfuric acid is most commonly used acid, but we can use any of these three options. That what is the acid catalyst we can use for the esterification of carboxylic acid. Now, the other things about this Fischer esterification is that this reaction is reversible, and by controlling the reaction conditions, we can increase the amount of ester. As you all know, that there is an equilibrium which established from the reactant to the direction of the product one. So when we say that this is a reversible reaction, so there are the equal chances of the product to go back into its original or its starting form. So we can control the direction, and if we are interested that we can get the maximum yield or maximum amount of that ester, or we can convert the higher amount of the carboxylic acid into the ester, so we can control the condition. Now the best two approaches to which we can utilize to enhance or increase the yield of the ester, that the maximum of carboxylic acid can convert into the ester. In usual reaction conditions, when we talk about when we are taking the 1 mole of alcohol and we are reacting it with 1 mole of the carboxylic acid, so what we usually have that we got approximately 67% of ester, and the rest of the 33% remain um, unconverted, and it remain in the carboxylic acid form. So this has not converted into the ester one. So if we one thing is that if we can increase the high amount of the alcohol, or we are using the alcohol in excess, if this is inexpensive, then we can easily forward the reaction direction into the forward, means that we will have the higher amount of the ester. Now the second approach is this, that we can use the way to remove the water, because in this reaction the water is produced as a byproduct. So if this water is basically diluting this reaction, and if we evaporate it simultaneously during the reaction, so this is easier for us to get the esters in a higher amount. So in most common cases, we utilize the approach one, that we use the alcohol in excess. So ethyl alcohol or ethanol or methanol are the most common alcohols which we use. If we are have to move in a synthesis from the ester to other conversions, or we are interested in to another end product which may need some more steps of the synthesis, and there are the further more conversion from ester to amides, or the cyclization, or any of the reaction, right? But if you are interested to stop at this step, and you are interested to recover that ester as your product, and you have to work on that one, so then it means whatever the ester has asked to you, and you are interested in the product, so then you can use according to that, what will be the alcohol you will use, and what will be the carboxylic acid. So you can interchange whatever depending on the availability and the price of the reagent. So if the particular substitution or the particular carboxylic acid is available, so you can select accordingly the alcohol, that what is your desired ester which you wanted to produce or you wanted to synthesize. Now we'll go for the mechanism. So this mechanism is, if you just firstly concentrate on this slide, so I assure you that you will you are able to easily draw the mechanism, and you can understand the mechanism, that how this acid catalyzed acid reaction go for the esterification. Now the beauty of the organic chemistry and the key to get the concept of these mechanism is this, that you should know the condition. So if you there are the hundreds of reactions for the esters you can generate by using the same reaction conditions. So you can change the carboxylic acid, you can change the alcohol, so the mechanism will remain same if you are using the same kind of reaction condition, excluding your alcohol. We are using the acid, right? And we are using that alcohol as a solvent. So you should know if the acid catalyzed reaction is there. So how, what are the different key steps, and what are the events which are happening. So if you know the sequence, and if you know the nucleophile, if you know the electrophile, if you know what is the most stable form, so you can easily draw the mechanism. So there is nothing to worry about, that you can't cope or you can't get the idea how the mechanism will draw, right? So I just need your attention. If you pay on it and you can understand, so this is nothing that you have to memorize the reaction mechanism for every reaction of the ester. So you just one time you have to understand it, what is the reaction condition and how your carbonyl carbon and oxygen is behaving, and what will attack after that step. So you can draw for any carboxylic acid, you can draw the mechanism. So here I'm giving using the same acid as an example, which I have showed you in the previous slide. So this is acetic acid, the very simple and the basic acid here. So we are reacting it with ethanol, which is ethyl alcohol, and you're using the acid as which is a sulfuric acid. So this is the shorter mechanism, but below that I have drawn in the more detail to give you the idea that what are the different events which are happening in this mechanism. So in a shorter version, what is happening, that there is a reaction between the firstly is the proton, right, which will be captured. So there is the formation of the nucleophile and electrophile. So they both will combine, there will be attack on it, and overall we will get our final product, which is the ethyl acetate. This is the common name of this ester, and if you will name it as IUPAC name, so this is ethyl ethanoate, right? So ATE, 8 is to mention, is used as a suffix for mentioning the ester class, because this is not the continuous chain. So what we do is that we write this alkyl chain as prefix, as a substitution, right? And the rest of which is our major functional group, so that chain will be counted, and we will write its name as a parent name, and that will be the suffix. We will use 8 for the ester one. So here this is the 1 and 2 carbon chain, so this is the ethyl, right? And 8 is mentioning that there is a carbonyl, and then next to the carbonyl there is another oxygen, right? So now we know this is the 1 and 2 carbon chain. For any of the carbonyl compounds, and right now we are talking about the carboxylic acid, so this carbonyl will be the member of that chain, because it has the carbon. We are not taking in account this oxygen because this is not the carbon chain, so that is breaking that chain. So now 1 2 carbon chain is there, and the 1 and 2 carbon chain is there. So this is the ethyl, and this is again the ethanoate, right? So this is ethanoate. 8 is for the ester. So that was how we can name any of the ester. Now we'll talk about to the mechanism. So when we are using the acidic condition, so it means in our reaction mixture there is the number of hydrogen ions which are available. So this is the acidic solution, right? So this is acidic medium. So that could be the water, but right now we are using the alcohol here. So there is the acid in alcoholic medium. So this is making it more protonated medium, or the reaction conditions. So there is plenty of hydrogen ions available. So what will happen? So this is a carbonyl, and this oxygen has the non-bonded electron. So that can make a bond with the hydrogen, because it has a good affinity for this H positive, right? So now after taking up that proton, what it will go for, because oxygen was already utilizing its 2 unpaired electron with the carbon through the 2 covalent bonds. So now this is making another 3rd bond with the hydrogen. So that's why this is sharing its electron pair here. So that's why it's getting the positive charge. Now, this is the intermediate which has formed. Now we know in the system there is the alcohol, and this oxygen is the nucleophile because it is rich in electron. So what it can do is that this oxygen has to adjust its positive charge. So that's why it is taking back its pi electron from the carbon, making this carbon as electropositive, right? And this will be the electrophile, as in this short version I have written that one, right? So this C positive is forming by giving that pi electron back to the oxygen. So now this oxygen hydroxyl oxygen is basically attacking on this carbon to make the bond and to satisfy its bonding. This is a nucleophile and this is the electrophile here. Now, what is the next formation or the structure of that compound is, which is forming in our reaction system is, this is the OH, right? There is a hydroxyl, and now this was the ester formation, that there is this O and ethanol group has attached, and there was already hydrogen which was initially attached to that one. So I have mentioned it as hydrogen to make it more visible that how that will depart or how this will cleave from that compound, right? So this is an intermediate structure which is the ester but has the two hydroxyl groups. So this is a diol structure. Now, in the system, we have the alcohol, which we are using not only as a reactant, but it is also using as a solvent system. So any kind of reaction in which the reactant is also as a solvent, so this is called the solvolysis. And when that solvent and reactant is a water, so then we use the term hydrolysis, right? So this is a solvolysis also, because this alcohol is not only the reactant, but it is also the solvent one. So now this will take up that extra proton from this one, and this is making this hydronium species where there is the alcohol with one extra hydrogen, and this oxygen is getting the positive charge, but right now this is stabilizing this side of this molecule, right? So now in our system, as we know, this is here, so I have just shortened that line structure into this C2H5, so don't confuse with that one. So now what is happening to this is that this H and this OH, now they will go for the structural rearrangements, and this OH can capture this extra proton because it also has to stabilize its structure, because this oxygen is not pleased to having this H, this positive charge, it is not in its stable form. So whenever we are writing the reaction mechanism, we have to see the sites, we have to see the points where there is a possibility, where there is any of the atom or the structure is not in a stable form. So it will definitely go for its most stable form. And that is basically the trigger and the point where this is showing some kind of reactivity. So now this hydroxyl will capture this proton, and there will be the removal of the water, right? In some literature, you may see the mechanism in a version that you can just combine that proton and you can write OH2, and then in the next step, you can cleave that bond as a OH2. But right now, I'm managing these both steps in that version, because this is happening in the same way that this bond is breaking. This is approaching here, and this bond will weaken, and that will cleave as a water molecule. So now this is the structure form. Now it is having the ester, but still the carbonyl oxygen is having the hydrogen here, because it has make a double bond with the carbon through its non-bonded electrons. Now this bond is getting weaker, and the oxygen is no more interested to keep that hydrogen. But of course, this hydrogen will only be removed if there is in the reaction system there is a species which can easily capture that proton. And we know there is alcohol, and this hydroxyl side, this oxygen is can easily take up that extra proton from this environment, because this carbonyl is in a more stronger bonding with this carbon, and this OH is a good nucleophile, so that can capture that proton here. So now after this rearrangement and this hydrogen transfer or the removal, so we will get finally our ester, and this is the ethyl ethanoate. So if I ask you any of the ester product, so you should know that what would be your selection as a carboxylic acid, and if any of the species you have to fix. For example, if I say that you have to do the you have to prepare the ethyl pentanoate, so you should know that what will be your carboxylic acid and what of kind of alcohol you will choose. So according to your product desire or an objective, you can select the alcohol and the carboxylic acid. So the mechanism will remain same. So you just have to focus on that one. So in this mechanism, there are the 5 key steps. One is the first is the protonation. So always when we have the acid catalyzed reaction, so the first step will be the protonation. If especially in a case when we have such kind of functionality, which is a carbonyl, and this oxygen can easily take the H positive ion with itself. So the second one is obviously something is getting in the formation that is getting deficient in electrons, so this is converting into the carbocation, and there's a nucleophile, so there will be the reaction between the nucleophile and electrophile. So this is nucleophilic addition. Then there is the proton transfer, then there is a removal of water, then there is a removal of exoproton. Now we go for the experimental setup. It is just to illustrate you and to recall you your lab also, that how we can prepare in our lab the esters. So that is not the big deal. So you can easily synthesize in your lab. So what you need is that you need the round bottom flask, and as I told you, that this reaction is through the reflux. So it means that you have to heat your reaction mixture at the point that start boiling, and through the condenser we are cooling down that reaction mixture, and that will condense back. So that's why this is called the reflux. So in reflux we boil it, and when the fumes are formed of the product, so they are coming back, so they are getting the more interaction and many of the cycles of these reactions to convert the whole of the carboxylic acid into the product one. Now after completing that reaction and ensuring it through the TLC, what we do is we have to work up our reaction. So any reaction need a workup. So not necessarily did you have to go for the solvent extraction. You can sometime you have to just filter it out. Sometime you have to go for the rotary evaporation, and sometime you need the solvent extraction when your product is soluble in organic solvent and you're using the organic solvent here. So for this reaction, what we do is that we add, after cooling this at the room temperature, what we do is after neutralization of this reaction mixture, what we do is we add the diethyl ether. And the diethyl ether we use is because most of the esters has a very low boiling point. So that's why we prefer to use the solvent, the diethyl ether, because it has a very low boiling point. So that's why it is easily that this is not damaging, its evaporation is not damaging our product, so we can easily extract our ester product here. So now we will separate it out. So as diethyl ether layer will be at the upper layer, and at the bottom there will be the aqueous medium, because diethyl ether has the low density as compared to the water. So we can just separate our both layers, aqueous and our diethyl ether layer. So in diethyl ether we have our ester. So after evaporating diethyl ether, we will get our ester one. So for this, because this is the reference of one of my paper in which we have discussed the synthetic method, because we have set up the reaction conditions where we were able to get the 90% yield of our ester. So you can check out this paper if you are interested, that what is the ratio we should choose for the carboxylic acid versus alcohol and the amount of sulfuric acid. Now the next is the second esterification method, is the formation of methyl ester using diazomethane. Treating a carboxylic acid with diazomethane, usually in ether solution, converts the carboxylic acid under mild conditions and in very high yield to its methyl ester. So this is particularly when we are interested to utilize in a very mild condition. We are not interested in any of the acidic medium and in a high yield, though there are the very high toxic profile of this diazomethane. So this is the method which we utilize. So this is the overall reaction, that we will get the methyl ester because we are using the diazomethane here, and the nitrogen gas will be evolved as the byproduct here. Now we will see the mechanism. So the reaction of carboxylic acid with diazomethane occur in two steps. This is comparatively simpler in a way that it involves the very few steps as compared to the Fischer esterification, but in lab this is more difficult to handle as compared to the Fischer esterification. So the first step is take a proton away. So the diazomethane do exist in that form. So there is the nitrogen, triple bond nitrogen, and we know the nitrogen has the one non-bonded and the lone pair. Now this nitrogen, each nitrogen can make the 3 bonds, but here the nitrogen is making an extra bond with the CH2, right? And that's why this is getting the positive charge, and now this is in a quaternary form. Quaternary form means this is in a 4 bond with having the one positive charge, and there is a CH2 which is still deficient with the one hydrogen, right? So it has completed its octet by taking up the electron. So this is the negatively charged. So this is balancing each other. So before going into that detail, I wanted to show that what are the contributing structure and of this diazomethane. So how this is, they do exist in the both forms. So these are the two hybrid of resonance contributing structures. So it do exist as negative positive charge, and the other way is that the both nitrogens have the double and double bond with each other, and this nitrogen is positive and this negative is shifted to that nitrogen. So in both way that do exist, but of course when we are treating it under certain reaction conditions, so that will go for the best feasible form where it can go for the further reaction. So now we have written it as the methyl as a negatively charged side, and the nitrogen, central nitrogen, is the positive one. Now what is happening, that this negative, now this will behave as a nucleophile, and that will abstract that proton from this one, and this bond will weaken, and this electron will shift to the oxygen. So here that is carboxylate anion which will be formed. So this is the O negative, and there is the methyl diazonium cation. So this is the positive one, right? So now this has the nucleophile which has formed after treating with the diazomethane. Now the second step is this one, because we are using that reagent and this is still in the system. So what it will do is that it has taken up initially that proton from this side, and this was the methyl diazonium cation, and now this bond will broken. Now this oxygen as a nucleophile will attack on it, and because this carbon will now be the electrophilic carbon after getting deficient in electron because of the breakage of that bond. So this will get the positive, and this negative oxygen, the cationic oxygen, will attack on it, and that is taking up that alkyl or the methyl group with that one, right? So this is the SN2 mechanism. So what is the SN2 type reaction? So you should just have to check out it again, that in this is the simultaneously this is happening. So these both reactants are basically in the rate determining step, and they are happening in a same time. So there is no stable intermediate which has formed. So now this is the ester which has formed, and in that case we will only get the methyl esters of that carboxylic acid, and the nitrogen is removed as a byproduct here. Now, this was the mechanism of the second reaction. Something about the applications of the esters. So esters as a flavoring agent. So flavoring agents are the largest class of the food additives, and they are used in the perfumeries, they are using in the foods, beverages, and a very big industry of these flavoring agents. So in most cases, these flavoring agents were extracted from the plant sources with of that value of that fruit or plant, or whose flavor is desired, and the number of flavoring agents are the synthetic one. So they are the equal. There are a larger number of the flavors which have laboratory, which are synthesized in the labs, and they are available from the natural sources as well, depending on that what kind of flavoring agent we need. So usually they have, in some cases they have the very complex structures, so more than one and 3 or 10 complex structures which are giving the particular aroma to that one. But a large number of flavoring agents have synthesized industrially. So I have mentioned few of the esters which to give you the idea that what particular aroma they have, what particular flavor they have, and you can have in that product which are having that flavor. So if you just go for their composition, so you will see that they have mentioned these esters. So if you just go for any of the cosmetics and any of the product, and you check their labels where they have mentioned their ingredients, so you will see that the products do have more than one esters. So they are the blend of these esters are basically giving the particular aroma of that product. So the methyl butyl acetate, or its common name is isopentyl acetate, so this give you the banana flavor. Now the octyl acetate give you the orange flavor, methyl butanoate give you the apple flavor, ethyl butanoate give you the pineapple flavor, and there is the methyl anthranilate, or you can say the methyl 2-aminobenzoate. This give you the grape flavor. So this is the very interesting, and it is very pleasant experiment to do, because whenever you convert the carboxylic acid into the ester, so without smelling it consciously and deliberately, yeah, there will be the instinct smell. You can feel that there is a pleasant smell from that carboxylic acid, because that has converted into the ester one. Now, at last, there is a task for you, and you have to attempt that one for your practice. So the first question is this, that give the expected organic product when phenyl acetic acid is treated with each reagent. So I have given you the one case is the methanol and the catalyst. So this is basically through the Fischer esterification. The second one is the diazomethane, and the both we already have discussed. So you have to draw their mechanism, right? Their mechanism and the product by treating with the phenyl acetic acid. So the ester is same, but now the reaction conditions are different. Now the second question is this, show how to prepare pentanoic acid from each compound. So I have given you the two alcohols. One is the 1-pentanol and another one is the 1-butanol. So your product, I already have told you that the product will be the pentanoic acid, right? So you just have to go for that, what would be your product if you just mix that one, right? So sorry, you can just change that one, that if you treat the pentanoic acid with the 1-pentanol and you treat the pentanoic acid with the 1-butanol, so what would be your final product, right? So if you have a question, you can ask me. So that was all for today. Thank you. Have a good day.